Welcome to solverfy.
In this problem, we are given kind of the inverse of what we've been asked for in the past. So we want to determine the angular velocity of the flywheel, which will produce an amplitude of a quarter meter or quarter inch. So we have our unbalanced mass is 1/4 pound divided by gravity. Its eccentricity, or its offset from the center axis of rotation, is 10 inches or 5/6 of a foot. And we don't know what the excitation frequency is because we don't know how fast it would be spinning to cause an amplitude that is 1/4 of an inch. Now we can take, let's see here, we take our spring constant, which gives us our natural frequency. We then plug into our equation for the amplitude of the response, which is the amplitude of the force. So again, we have omega squared in here, divided by the stiffness, all divided by 1 minus the amplitude of the excitation frequency squared divided by the natural frequency. And that we want to be 1/4 inch. So this turns out to give us, actually, let's see here, I think did I write down, there actually should be a couple of solutions here. Let's see here. I didn't actually calculate the other solution. There should be another solution to this also, one that's above the natural frequency, because remember, we have something that's coming up like this and then coming back down, and so we're somewhere in this region here where we should have two solutions. Let me actually try to figure that out for you in real time here. So let's see here, 0.00, yeah, and omega squared divided by 1800, all divided by 1 minus omega squared divided by 19.7 squared. Okay, let's see if that looks right. Yes. And so we want that to be equal to 0.25 divided by 12. And I want to solve that all for the natural frequency. And let's see here. Oh, not the natural frequency, the excitation frequency. And come on. Sure why it's yeah, so well, no, let's see here, we get 19 point actually it's closer to 19.1. Actually, I guess we only get one solution. Thought we should get two. Well, we get the opposite one. Of course, we get the, well, that's why I'm thinking, because I'm thinking we get two solutions because of this squared here, but they're actually just plus and minus, which means that it could be spinning either way. So it's actually closer to 19.1 here, 19.07. So again, there should be one that's above. Oh, I know why. Because we can also have this a negative. Because I didn't consider the absolute value here. So when the forcing frequency is above the natural frequency, we can have this would be negative. So I need to actually solve the case where it's this amplitude in here is minus this. So what is that case? That case is 20. Let's see, 20.4 So we could either be slightly below or slightly above the natural frequency to get this amplitude.